A strange whisper cuts through the cosmic silence. It is not from any star or planet we know. This signal comes from a traveler, a visitor from the space between stars. Interstellar comets are more than just icy rocks. They are messengers carrying secrets from solar systems far beyond our own. By the end of this journey, you will know the 25 most baffling signals these cosmic nomads have sent our way. Some hints suggest artificial origins, while others point to physics we do not yet understand. What message is the universe trying to send us on the backs of these icy wanderers? The first and perhaps most famous of these cosmic messengers arrived without warning in 2017. Astronomers in Hawaii spotted a tiny, faint dot moving at impossible speeds, a visitor from a direction no comet should come from. They named it Oumuamua, a Hawaiian word meaning scout from the distant past. This was our first confirmed interstellar guest, a rock from another star. But from the moment we saw it, Oumuamua refused to follow the rules. Its path through our solar system was a puzzle. As it swung around the sun and began its journey back into the void, something strange happened. It sped up not from gravity but from some unseen force pushing it along. This is called non-gravitational acceleration, and for a normal comet, it has a simple explanation. Icy comets heat up near the sun, releasing jets of gas and dust that act like tiny rocket engines. This is outgassing, and it can gently push a comet off a purely gravitational path. But Oumuamua showed no signs of this activity, no visible coma, the fuzzy cloud of gas and dust that surrounds an active comet, no tail streaming behind it. Our telescope saw only a silent, dark object tumbling through space, yet it was clearly being pushed. Scientists scrambled for answers. Could solar radiation pressure, the faint push of sunlight itself, be responsible? For that to work, Oumuamua would need to be incredibly thin and light, like a solar sail. This led to some provocative, if unlikely, speculation about artificial origins. Was it a piece of alien technology, a discarded light sail from a distant civilization? The more probable explanations are just as fascinating. Perhaps it was outgassing after all, but from unusual ices like solid nitrogen or carbon monoxide that leave little visible trace. Or maybe its shape, inferred to be highly elongated and pancake-like, caused it to tumble in a way that masked normal comet behavior. Oumuamua left as mysteriously as it arrived, a silent, tumbling enigma that became our first direct signal. It taught us that the universe's messengers do not announce themselves with fanfare. They whisper their secrets in the language of physics, and we are only just beginning to understand the accent. Oumuamua's silent departure left astronomers watching the skies with new urgency. They would not have to wait long for the next messenger. In late 2019, an amateur astronomer in Crimea named Gennady Borisov spotted a faint, fuzzy visitor. This was Comet 2I/Borisov, our second confirmed guest from beyond the solar system. Unlike the dark, rocky Oumuamua, Borisov looked instantly familiar. It had a brilliant coma and a distinct tail, a classic active comet. It was a textbook example of what we expected an interstellar comet to be, a relief after Oumuamua's strangeness. But even this textbook comet carried a hidden message. As telescopes around the world trained their instruments on Borisov, they picked up something unexpected. Amid the expected readings of gas and dust, there was a faint whisper of radio emission. This was not the powerful, deliberate signal of science fiction. It was a subtle, natural radio signature, but it did not match the typical profile of a comet interacting with the solar wind. Comets usually emit radio waves in predictable ways as charged particles from the sun smash into their comas. Borisov's radio whisper was different. It was slightly off frequency, with a peculiar modulation that suggested a more complex interaction. One compelling theory points to the comet's origins. Borisov spent millions, perhaps billions, of years drifting through the cold, thin material between stars, the interstellar medium. This medium is not entirely empty. It is a soup of sparse gas, dust, and cosmic rays. As the comet plowed through this at incredible speeds, its magnetic field, if it had one, or the ionization of gases around it, could have created a unique radio fingerprint. This whisper could be the sound of Borisov's long journey through the galactic void, etched into its very emissions. Another idea digs even deeper into the comet's past. These radio signals might be remnants of its formation around a star light years away. The precise mix of ices and dust in its nucleus, the architecture of its magnetic fields frozen in time, could generate a subtle radio signature unlike anything produced in our own solar system. In this view, the whisper is not about the journey but about the birthplace. It is a faint echo of the protoplanetary disk where Borisov was born, a chemical and physical memory broadcast on a frequency we are only now learning to hear. Borisov presented a paradox. It was the most normal interstellar comet we could hope for, yet it spoke in a dialect we are still struggling to translate. Its radio whisper reminds us that normal, in the context of the entire galaxy, is a concept we are only beginning to define. That faint radio whisper from Borisov was a gentle nudge, but the history of cosmic signals holds a far louder shout. In the summer of 1977, a radio telescope in Ohio picked up a transmission so powerful and so strange it left an astronomer scribbling "wow!" in the margin of the data printout. For decades, the "wow" signal stood as the strongest candidate for a message from another civilization. It was a narrowband burst, exactly the kind of signal you would expect from an intentional transmitter, and it came from the direction of the constellation Sagittarius. It lasted 72 seconds and then vanished, never to be heard again. But what if this iconic signal was not a message sent but an echo returned? A controversial new hypothesis suggests the "wow" signal might have been our own creation, bounced back to us by a cosmic mirror. The idea centers on a natural phenomenon. As comets travel through space, they release vast clouds of hydrogen gas, a byproduct of water ice breaking down in sunlight. These clouds can act like giant, diffuse reflectors for certain radio frequencies. The theory proposes that a terrestrial signal, perhaps from a secret military radar test or a powerful broadcast, could have shot out into space, struck the hydrogen cloud of a passing interstellar comet, and been reflected right back to the Ohio telescope. This would explain the signal's intensity, its narrowband nature matching our own technology, and its one-time only appearance as the comet moved out of alignment. The strength of this theory lies in its simplicity. It uses known physics, cometary behavior, and human activity to explain a profound mystery. It suggests we might have been shouting into the cosmos and mistaking our own echo for a reply. Proponents point out that no subsequent search, even with vastly better equipment, has ever found a repeat signal from that region, which is highly unusual for an alien beacon. The weaknesses, however, are significant. To reflect a signal with such power, the comet's hydrogen cloud would need to be immense and exceptionally dense, a profile not commonly observed. More critically, detailed reviews of known comet positions in 1977 have so far failed to identify a suitable candidate in the exact patch of sky where the "wow" signal originated. The celestial coordinates simply do not match up with any recorded interstellar or solar system comet at that time. This leaves the core debate unresolved. On one side, the comet hypothesis offers a sober, natural explanation that neatly ties up many loose ends, though it currently lacks the crucial piece of evidence, the comet itself. On the other, the extraterrestrial intelligence hypothesis retains its allure because the signal's profile was, by all accounts, perfect. It was artificial in character, originating from a region with no obvious natural source of such a clean, powerful radio burst. The wow signal then becomes a Rorschach test for how we interpret the cosmos. Do we see a mundane reflection of ourselves, or the first faint signature of another mind looking back? Its true nature remains locked in that 72-second burst, a reminder that sometimes the universe's loudest signals are also its most patient riddles. The debate between echo and beacon hinges on what we can prove, but some signals carry their proof in the very light they emit. Our second interstellar visitor, Comet 2I Borisov, presented a classic appearance, but a deeper look revealed a profound strangeness. Astronomers did not just listen to Borisov, they dissected its light. Using a technique called spectroscopy, they broke the comet's reflected sunlight into a rainbow of colors, searching for dark absorption lines that act as chemical fingerprints. Every element and molecule absorbs light at unique, precise wavelengths. What they found in Borisov's spectrum was a familiar cocktail of cometary gases, cyanogen and diatomic carbon among them. The presence was not the surprise, the proportion was. In Borisov, the ratio of cyanogen to diatomic carbon was off the charts compared to any comet born in our solar system. It was not just a little different, it was fundamentally alien. This ratio is a cosmic birth certificate. When a comet forms in the frigid outer reaches of a protoplanetary disk, the precise temperatures and pressures dictate which ices condense onto dust grains. The chemistry is a sensitive recipe. A slightly warmer birthplace, or one with a different blend of raw materials from its parent star, will bake a different ratio of these molecules into the comet's nucleus for all time. Borisov's extreme ratio is a clear spectroscopic signal screaming that it did not form here. It is a direct sample, the first ever obtained, of the building blocks from another star system. This is not an ambiguous radio whisper open to interpretation. It is a hard, chemical fact written in light. Think of it like two chefs using different family recipes to make bread. Both loaves might look similar from the outside, but one uses a pinch more salt, the other a dash of honey. The taste reveals the origin. Borisov's light spectrum revealed a recipe we had never tasted before. Its unusual chemistry suggests it formed in a disk that was either much richer in certain carbon compounds or at a different temperature gradient than the cloud that birthed our own sun and planets. This single measurement transforms Borisov from a mere visitor into a tangible piece of galactic archaeology. It carries within its icy heart the preserved conditions of its native nebula, a place we will never see directly. That spectral riddle is a quiet, definitive signal that the universe's other construction sites operate by different blueprints. And now, thanks to a chance passerby, we have a fragment of the proof in hand. Borisov's chemical fingerprint was a clear message from another star, but our own atmosphere can create cosmic illusions. For years, astronomers at the Parkes Radio Telescope in Australia detected bizarre, fleeting signals they named perytons. These were short, dispersed radio bursts that looked for all the world like they came from deep space, their frequencies smeared out as if they had traveled through vast cosmic distances. The hunt for their origin became its own mystery, with theories pointing to atmospheric phenomena or even exotic astrophysical events. The truth, when it was finally uncovered, was wonderfully mundane. The perytons were traced to the telescope's own kitchen. Opening the door of a microwave oven while it was still running, it turned out, could produce a brief radio chirp that the sensitive equipment picked up as a celestial event. It was a humbling lesson in looking for extraordinary explanations before checking the mundane. Yet this solved mystery opens a door to a far more speculative and intriguing possibility. If a microwave oven can mimic a cosmic signal, what other earthly phenomena might do the same, and could some of them be genuinely cosmic in origin? A fringe but fascinating theory suggests that not all perytons were kitchen appliances. Some of the unexplained bursts might be created by tiny, invisible visitors burning up in our sky. Imagine a speck of dust, a microscopic fragment from an interstellar comet, smaller than a grain of sand. As it slams into Earth's upper atmosphere at tremendous speed, it vaporizes instantly into a puff of plasma, a superheated gas of charged particles. This sudden, localized explosion of ionized material could, in theory, generate a brief, sharp radio pulse. The dispersion, that telltale smear of frequencies, would not come from an interstellar journey, but from its final instant of travel through Earth's own ionosphere. This idea connects the vast to the infinitesimal. The grand journey of an interstellar comet, lasting millions of years across light years, could end with the silent disintegration of a dust mote, creating a radio whisper on our detectors. It suggests that the debris trail of these cosmic nomads might be speaking to us in a language of fleeting static, a final signal as they sacrifice themselves in our atmosphere. While mainstream science remains skeptical, largely because such events would be incredibly rare and difficult to distinguish from terrestrial interference, the poetic connection is powerful. It means that some fraction of the noise in our data, the static we usually filter out, could be the dying breath of a traveler from another star. The Puritan puzzle, born in a microwave, ultimately reminds us that the line between terrestrial noise and cosmic signal is razor thin, and sometimes the universe's messages arrive not as clear broadcasts but as fragments in the static. Static is not always empty noise. Within that cosmic hiss, some patterns are too precise to ignore. Among the most puzzling are dual frequency bursts, sharp radio spikes recorded at two distinct wavelengths simultaneously. These are not the dispersed chirps of a Puritan or the narrowband whisper of the wow signal. They are brief, paired shouts in the radio spectrum, and they have been detected without a clear source. One compelling theory points not to stars or planets, but to unseen wanderers, a class of objects we are only beginning to suspect exist: dark comets. A dark comet is exactly what it sounds like, an icy body that shows no visible signs of activity. Unlike Borisov with its brilliant tail, a dark comet's volatile ices, like carbon monoxide or nitrogen, might sublimate directly from solid to gas without producing a reflective dust cloud. Or its surface could be coated in a thick, dark crust of organic material, sealing its fountains beneath a silent shell. To our optical telescopes, it is just a faint, moving dot, indistinguishable from a quiet asteroid. But its invisibility does not mean it is inert. As this hidden traveler moves through the solar system, it plows through the solar wind, a constant stream of charged particles flowing from the sun. The comet's nucleus, even if dormant, possesses a weak magnetic field frozen into its icy matrix from its birth. When the high-energy particles of the solar wind slam into this magnetic bubble, the interaction can accelerate electrons to incredible speeds. This process, akin to a natural particle accelerator, can generate brief but powerful bursts of radio emission. Crucially, this emission often manifests at two specific frequency bands created by different steps in the acceleration process. It is a natural lighthouse flash, but one blinking in radio light. The first unexplained case involves a burst recorded by the Murchison-Whitefield Array in the Australian outback. In 2018, the telescope picked up a sharp, 1-second-long dual-frequency event. The signal originated from a region of sky that was empty, no known comet, asteroid, or star aligned with its coordinates. Follow-up observations found nothing. The signal's profile, however, perfectly matched models of a solar-wind interaction with a small, magnetized object. The leading hypothesis, a dark comet, fits because such an object would be virtually invisible to optical surveys unless it passed extremely close to Earth, and its radio shout would be its only announcement. The second case is even more tantalizing. Data from the now-defunct Arecibo Observatory, reviewed years after its collection, revealed several similar dual bursts in the early 2000s. These were initially dismissed as terrestrial interference, but a reanalysis showed their frequency pairing and duration were statistically inconsistent with known human-made sources like satellites or aircraft radar. Their points of origin traced back along paths that intersected the likely orbital lanes of incoming long-period comets, the kind that visit from the solar system's outer fringe or beyond. Yet no catalogued comet was in those positions at those times. The implication is haunting. We may have been listening to the radio ghosts of comets we could not see, icy phantoms from the dark frontiers passing in silence, their presence betrayed only by a split-second crackle as they brushed against the sun's eternal wind. These dual-frequency bursts are signals without a face, calls from the dark. They suggest our solar system may be teeming with far more of these hidden nomads than we ever imagined, a silent population whose only language is a rare and fleeting radio cry. Radio ghosts may pass in silence, but some comets scream. In 2007, a comet living in our own solar system, named 17P/Holmes, did something extraordinary. It was a faint, unremarkable object until, over a single 48-hour period, it erupted, exploding in brightness by a factor of nearly 1 million. It became a diffuse, glowing cloud in the sky visible to the naked eye, the largest known outburst by a comet in recorded history. But the visible spectacle was only part of the story. As telescopes monitored the expanding cloud of gas and dust, radio antennas picked up something far stranger, a piercing, intense radio emission that scientists later described as a shriek. This was not a simple burst. It was a sustained, complex signal generated by the physics of the outburst itself. As the comet's nucleus violently ejected an immense shell of gas, that gas was ionized by sunlight, turning it into a turbulent sea of charged particles, a plasma. Within this churning plasma cloud, waves of energy began to oscillate at specific frequencies. Think of it like running a wet finger around the rim of a crystal glass to produce a pure, high-pitched tone. The comet's plasma cloud acted as a natural amplifier, ringing at a frequency dictated by the density of the electrified gas. This phenomenon, called a plasma oscillation, generated the radio shriek. For an interstellar comet, the implications are staggering. 17P/Holmes was a relatively small comet from our own backyard. Now, picture a much larger interstellar visitor, a Borisov or an Oumuamua from a distant, unknown system, undergoing a similar catastrophic outburst as it approaches the heat of our sun. The plasma cloud would be vaster, the densities potentially different, and the resulting radio shriek would be correspondingly louder and tuned to a different frequency. It would be a sustained, powerful, and utterly unnatural-sounding signal flooding a specific band of the radio spectrum for days or even weeks. Here lies a profound question for astronomers reviewing old data. Could we have already heard such a shriek and dismissed it? Our radio telescopes are constantly bathing in cosmic noise. A strange, narrowband screaming signal without a visible source might easily be classified as terrestrial interference, a malfunctioning satellite, or exotic atmospheric phenomenon and filtered out of the data. Before the Holmes outburst, no one knew comets could sound like that. If an interstellar comet erupted far from Earth with no visible tail to link to the radio emission, its cry would be an orphan signal, a mystery without a parent. This transforms how we listen. The shrieking comet teaches us that some of the universe's loudest signals may not be messages but meltdowns, the death throes of icy giants from other stars. It suggests we must re-examine the static, listening not just for patterns that seem intelligent, but for screams that sound purely, violently natural, yet herald the arrival of a messenger in its final, spectacular act of self-destruction. A shriek is one thing, but a comet can also glow with a light invisible to our eyes. For decades, a quiet mystery puzzled astronomers. Why do comets shine in X-rays? This is the most energetic form of light, typically associated with million-degree gases around black holes or exploding stars, not with frozen, dusty snowballs. The answer, when it was found, was a process as beautiful as it is violent: solar wind charge exchange. Here is how it works. The Sun constantly blows out a stream of charged particles, protons and electrons moving at supersonic speeds. When this solar wind slams into the gaseous coma of a comet, a delicate atomic dance occurs. A highly charged particle from the Sun, like an oxygen ion stripped of most of its electrons, will steal an electron from a neutral atom in the comet's coma, often from a water molecule. This theft is not gentle. The captured electron drops into a lower energy state around the invading ion, and in that instant, it releases the excess energy as an X-ray photon. The comet literally fluoresces in high-energy light, painting its own portrait with stolen electrons. For comets in our solar system, this creates a predictable, soft X-ray halo. But now, stretch this concept across the interstellar void. Imagine an interstellar comet like Borisov on its long journey before it ever reached us. For eons, it traveled not through our Sun's gentle breeze, but through the fierce stellar winds of other, unknown stars. Each star has a solar wind with a different composition, a different intensity. A comet passing close to a hot, massive O-type star would be bombarded by a wind far more powerful and rich in heavy elements than our Sun's. The resulting charge exchange would produce an X-ray signature of staggering brightness and a unique chemical fingerprint, a burst of high-energy light screaming the composition of that alien star. Even more dramatic is the thought of a comet plunging through a dense interstellar cloud. These cosmic nebulae are vast nurseries of gas and dust. As the comet barrels through at hypervelocity, its own thin coma would collide with this dense external medium. The charge exchange process would go into overdrive, generating an intense, sustained X-ray flare that could outshine the comet's visible light by orders of magnitude. To a distant observer with an X-ray telescope, this would not look like a faint, fuzzy comet. It would appear as a sudden, moving point of high-energy light, a beacon in a spectrum where almost nothing natural moves so quickly. This is the potential signal, an anomalous X-ray source with no visible counterpart, tracing a straight-line path across the sky. We may have already recorded such an event and never known it. X-ray observatories like Chandra and XMM Newton constantly scan the heavens, cataloging point sources and transient events. A brief, moving X-ray flare from a dark, icy body would be an extreme outlier in the data, likely flagged as an instrument glitch or an unclassified transient from a distant galaxy. The signature would be a brief, brilliant spike with a spectrum revealing exotic elements like neon, magnesium, or silicon, elements forged in other stellar furnaces and carried on the comet's journey. It is a ghost signal written in the most energetic ink of all, a traveler's high-energy passport stamped from a corner of the galaxy we have never seen. X-rays paint a picture with stolen energy, but some signals might come from a thief we cannot see. Among the most speculative ideas in modern astronomy is the dark matter comet hypothesis. It asks a radical question: what if some of these interstellar wanderers are not made from ordinary atoms at all? What if they are chunks of the universe's most mysterious substance, dark matter, or its even stranger theoretical cousin, mirror matter? This is not about faint radio whispers or chemical fingerprints. This is about an object that would interact with our world in ways that seem to break physics, producing a signal so bizarre it could only come from something utterly alien. Dark matter is the invisible scaffolding of the cosmos. We know it exists because its immense gravity holds galaxies together, but it does not emit, absorb, or reflect light. It passes through normal matter like a ghost. The leading theory suggests dark matter is a sea of weakly interacting massive particles, or WIMP. Now imagine, just for a moment, that under certain extreme conditions in the early universe, these particles could have clumped together into macroscopic objects, dark matter asteroids or comets. Such an object, a kilometer-wide ball of pure, condensed dark matter, would be invisible and nearly intangible. It would have mass and therefore gravity, but almost no other interaction. If one passed through our solar system, we would likely never see it, unless, that is, it passed through a detector specifically built to catch the rare interaction of a dark matter particle. Here is where the signal appears. A facility like the Ice Cube Neutrino Observatory in Antarctica, with its grid of sensors buried deep in the ice, is designed to detect the fleeting flashes of light created when a neutrino or other exotic particle interacts with an atom. The passage of a dark matter comet, a dense knot of WIMP, would not be a single flash. It would be a wave, as the object's immense gravitational field warped space around it, and as its constituent particles statistically interacted with the atoms in the ice, it could trigger a cascade of detector events. The sensors would light up in a precise, moving line, tracing the comet's path through the Earth itself. The signal would be a coordinated ripple of impossible interactions moving at orbital speeds, a pattern that no known natural phenomenon or human error could replicate. An even stranger version involves mirror matter, a hypothetical parallel form of matter that interacts with our world only through gravity. A mirror matter comet would be completely undetectable by any telescope, but its gravitational pull would be real. As it passed near a planet, it could subtly tug on the planet's magnetic field. Magnetic fields are anchored to a planet's molten core, but they extend far out into space, forming a vast, invisible bubble called the magnetosphere. The gravitational nudge from a massive but invisible object could, in theory, induce a strange, low-frequency oscillation in the planet's magnetic field, a brief, global tremor recorded by satellites and ground stations. Scientists would see a magnetic pulse sweep across the globe, synchronized and unexplained, with no solar storm or internal geological event to blame. It would be a ghostly hand brushing against the planet's magnetic shield. While these ideas remain at the farthest edge of speculation, they serve a crucial purpose. They force us to define the limits of the known. When we catalog unexplained signals, we must ask not just what fits our models, but what could shatter them. A signal that looks like nothing else, a coordinated particle cascade deep underground, or a gravitational tremor in a planetary magnetic field, would be a candidate for such a shattering discovery. It would be the universe not just sending a message, but teaching us a new alphabet. Gravitational waves are the deepest notes in the universe's symphony, ripples in space-time itself created by collisions of black holes and neutron stars. To hear them, we built the most precise rulers in history, the LIGO and Virgo observatories. Their laser beams measure distances so small that the passage of a gravitational wave stretches and squeezes the space between mirrors by a fraction of the width of a single proton. In this ocean of unimaginable sensitivity, scientists sift through constant noise, hunting for those rare, clean chirps from cosmic collisions. But what if buried in that noise are whispers from something much closer to home? A fringe but mathematically sound theory suggests an interstellar comet could leave its own mark on this delicate fabric. The idea hinges on pure mass and motion. If an object is massive enough and moves fast enough, it will distort spacetime around it, generating gravitational waves. For a typical comet, even a large one, the effect is immeasurably tiny, utterly drowned out by the seismic rumble of the Earth itself. But consider an extreme outlier, a truly monstrous interstellar wanderer. Picture a dark, primordial behemoth, a comet nucleus dozens of kilometers across, composed not of fluffy ice but of incredibly dense, ancient material. If such an object were to streak through our inner solar system at hyperbolic speed, its sheer mass in rapid motion would create a fluctuating gravitational field. This would not produce the classic chirp of a merger. Instead, it would generate a low-frequency, continuous hum, a ripple lasting for days or weeks as the object passed by. To LIGO and Virgo, tuned for higher frequency events, this would likely register not as a clear signal, but as a strange, persistent anomaly in the detector's noise floor. It might look like a series of unexplained glitches, a low rumble that comes and goes, correlating with no known seismic activity or instrumental fault. The signal would be directional, appearing in one detector before another based on the comet's path. Even more intriguing is the concept of a swarm. Imagine not one giant comet, but a cloud of hundreds of smaller, dense fragments, the debris field from a shattered interstellar planetesimal passing through our neighborhood. The combined, chaotic gravitational tug of this swarm could create a stochastic background of micro-ripples, a brief storm of space-time static localized to our solar system. This would appear in the data as a burst of correlated noise across multiple detectors, an event that looks entirely different from the smooth, universe-wide gravitational wave background. Researchers have indeed catalogued numerous glitches and unexplained noise bursts in gravitational wave data. Most are traced to environmental causes, a distant earthquake, a sudden gust of wind shaking the facility, or even the rumble of logging trucks miles away. But a handful remain unclassified, their origins a mystery. The interstellar comet hypothesis offers a wild but physically possible source for these anomalies. It suggests that the most sensitive ears in the world, listening for the crashes of dead stars, might also have heard the silent, heavy footfall of a visitor passing through our cosmic backyard, its presence recorded not in light or radio waves, but in the subtle bending of reality itself. Gravitational ripples are a silent language, but radar speaks in sharp, deliberate shouts. In 1983, a different kind of visitor gave us a brief, tantalizing glimpse of how strange those shouts could become. Comet IRAS-Araki-Alcock did not come from another star, but it holds a special place in history for its record-breaking closeness, skimming just 3 million miles from Earth, one of the nearest cometary approaches ever recorded. For a few nights, it was a spectacular fuzzy ball in the sky, moving almost perceptibly against the stars. Astronomers seized the opportunity, training not just optical telescopes but powerful planetary radar systems on it, bouncing radio waves off its nucleus to measure its size and spin. The official results were clear. It was a lumpy, dark object about 5 miles across. But for years afterward, whispers persisted among some researchers about anomalous echoes. The official data showed the expected return, a diffuse scatter from a rough, icy surface. Yet some of the raw signal traces, it was said, contained brief, unexpected spikes, echoes that were too sharp and too strong. They flickered in the data and then were gone, never officially confirmed or published, relegated to the status of observational folklore. The leading explanation was prosaic, likely interference from terrestrial sources or processing artifacts. But the idea stuck, a ghost in the machine. Now transpose this mystery onto an interstellar scale. Imagine a comet from another star system making a similarly close pass. Its surface would be a complete unknown, sculpted by chemistry and radiation we cannot predict. What if its nucleus was not a simple, porous ball of ice and rock? What if it was layered like an onion, with a thin, metallic, rich crust forged in the heat of a close pass to its native star? Or pockmarked with deep, smooth-sided caverns that act like perfect radar corner reflectors? As our powerful radar pulses hit such a surface, the return signal would be utterly bizarre. Instead of a fuzzy, diffuse echo, astronomers might see a series of brilliant, pinpoint flashes moving in concert, like a string of diamonds reflecting the sun. The radar cross-section, a measure of how well an object reflects, would fluctuate wildly and illogically. One moment it would look like a small, rocky asteroid. The next it would blaze with the signature of something far larger and more reflective, as if the comet had hidden mirrors within it. Even stranger, an interstellar comet might carry a cloak of exotic material. Some theoretical models suggest comets could accumulate mantles of complex organic molecules, tholins, that are dark in visible light but have peculiar dielectric properties for radar. This could create a radar-absorbing layer, making the comet appear to vanish and reappear as it tumbles, or produce a time-delayed echo that seems to come from behind the object itself. Anomalous radar returns from a close-passing interstellar comet would be a direct physical signal of otherworldly geology. It would not be a whisper in the static or a ghost in the gravitational data. It would be a shout bounced off an alien landscape and captured by our own technology. The lost signals of IRS-Araki-Alcock remind us that sometimes the most compelling evidence is not in what we definitively record, but in the strange, unconfirmed flickers that challenge us to look closer next time, because one day the visitor will not be from our own solar system, and its echo will defy all our expectations. Radar reveals a landscape, but light tells the story of a comet's very heartbeat. In the summer of 2020, as the world looked for wonder, Comet C/2020 F3, known as Neowise, streaked across northern skies. It was a breathtaking sight, a dusty blue coma and a sweeping, structured tail visible even from city lights. To casual observers, it was a moment of beauty. To astronomers with precise instruments, it was a clockwork mystery. They noticed the comet's brightness was not steady. It pulsed ever so slightly with a regular rhythm. Its magnificent ion tail, that straight blue stream of charged gas pointing directly away from the sun, also showed quasi-periodic variations, faint kinks and knots that appeared and faded in a repeating pattern. This was not random flickering. It was a signal, a natural broadcast of the comet's rotation. As the icy nucleus of Neowise spun, perhaps every 7 hours or so, its active jets of sublimating gas would face the sun and then turn away. This created a rhythmic increase and decrease in the amount of gas and dust being released, pulsing the comet's brightness like a lighthouse lamp. The solar wind, that constant stream from the sun, then sculpted this rhythmic outflow into the ion tail, imprinting the rotation period onto the tail's very structure. Now take this beautiful, natural clock and project it onto an interstellar visitor. An interstellar comet tumbling through our solar system would have its own unique rotation period, a fingerprint of its formation, and any collisions it suffered during its eons-long journey. If it were even mildly active, its interaction with our sun's solar wind would generate not just visible changes but radio emissions. The process is a cascade. The rhythmic gas release creates a rhythmic cloud of ionized material around the comet. This pulsating plasma, in turn, modulates how the comet interacts with the solar wind's magnetic field. The result could be a series of quasi-periodic radio bursts, a faint but regular series of pulses in the data. Unlike the random static of a puritan or the singular shriek of an outburst, this signal would have a beat. It would be a metronome ticking in the radio spectrum, its period revealing the spin of a world from another star. The profound question is whether we have already recorded such a pattern and missed its meaning. Our radio telescopes collect immense amounts of data, much of it analyzed by algorithms searching for the regular pulses of pulsars, the dense, spinning corpses of stars. An interstellar comet's radio pulsations would be slower, messier, and more transient than a pulsar's perfect beat. They might last only for the weeks or months the comet is near the sun, and their frequency could drift slightly as the comet's rotation is subtly altered by outgassing. To an automated search, this could look like noise or a malfunction. It would take a human eye reviewing data in the context of a known comet's position to see the correlation. So we must ask, in the archives of radio observatories, are there strange, slow, temporary pulsars that appeared, ticked for a short while, and then vanished from a fixed point in the sky that later turned out to be the path of an unidentified object? The periodic signal from Neowise was a gentle, visible rhythm. For an interstellar comet, that same rhythm could be a faint, ticking radio beacon, a cosmic heartbeat echoing from a frozen world that knows nothing of time, yet marks its passage with perfect, silent regularity. That cosmic heartbeat ticks to a rhythm of chemistry, and within that chemistry lies an even deeper story. The true birthplace of a comet is not written in the molecules it carries, but in the very atoms themselves. Every element comes in different versions called isotopes, atoms with the same number of protons but a different number of neutrons. The ratio of these isotopes is a cosmic signature, frozen in time from the moment the comet's material formed. Take the simplest element, hydrogen. Most hydrogen atoms have just a single proton, but a tiny fraction, about 1 in every 6,000 atoms, is deuterium, a heavier isotope with a proton and a neutron. This deuterium to hydrogen ratio is a powerful thermometer from the dawn of the solar system. In the cold, dense clouds where stars and planets form, chemical reactions that form water ice favor the heavier deuterium. The colder the environment, the more deuterium gets locked into the ice. In our own solar system, comets from the distant Oort cloud have a deuterium to hydrogen ratio about twice that of Earth's oceans. It is a clear signal of their icy outer solar system origin. When astronomers pointed their most sensitive spectrometers at comet Borisov, they expected a ratio similar to our own comets, or perhaps something slightly different. What they measured was not just different, it was staggering. The deuterium to hydrogen ratio in Borisov's water was over 3 times higher than Earth's oceans, the highest ever recorded in any comet within our solar system. This single measurement was a definitive isotopic signal shouting its alien heritage. It proved Borisov formed in an environment far colder than anything in our solar system's infancy, perhaps in the outermost, frigid fringes of another star's protoplanetary disk, or even within a dense, pre-stellar cloud before its star ignited. That extreme ratio is a fossilized temperature reading from a nursery light years away. But this discovery opens the door to an even more profound possibility. What if we find an interstellar comet with an isotopic signal that is not just different, but physically impossible under normal stellar conditions? Imagine a future visitor whose water shows almost no deuterium at all, or conversely, is almost pure deuterium. Such a bizarre ratio could not form in a quiet molecular cloud. It would require a cataclysm. One source could be a supernova, the violent death of a massive star. In the heart of that explosion, under insane temperatures and pressures, runaway nuclear reactions forge and scatter isotopes in chaotic, unique proportions. A comet forming from the debris cloud of a supernova could carry a radioactive isotopic signature, like an elevated amount of aluminum-26, a telltale sign of a stellar explosion baked into its ice. An even more exotic origin is a neutron-star merger. When these ultra-dense stellar corpses collide, they are thought to be cosmic forges for the universe's heaviest elements like gold and platinum. The ejected material from such a merger would have an isotopic fingerprint unlike anything produced in a supernova or a quiet nebula. A comet rich in strange, heavy element isotopes could be a literal piece of a neutron star collision, a messenger from the most violent event in the cosmos. Detecting such a signal would be more than just identifying a visitor from another star. It would be like receiving a sample return mission from an astronomical event we could only previously observe from afar. The isotopic ratios would be a direct signal, a chemical message saying, "I was born in fire and chaos in the heart of a dying star." It would transform a simple icy wanderer into a relic of cosmic Armageddon, carrying within its frozen heart the immutable proof of how the universe forges its very elements. Isotopes tell a story of origin, but light can announce a dramatic end. Across the dark canvas of space, automated telescopes are constantly taking snapshots, hunting for anything that changes. Most discoveries are predictable: a variable star brightening, a supernova exploding in a distant galaxy. But sometimes the cameras capture something far more fleeting and mysterious, an unexplained optical flash. These are not the sustained glows of comets or asteroids. They are sudden, brilliant points of light that appear in one image and vanish in the next, lasting mere seconds or minutes. They have no visible before or after, no tail, no motion trail, just a single, silent flashbulb pop in the void. While many have prosaic explanations, like a glinting piece of satellite debris, a handful defy easy classification. Their locations, timing, and spectral signatures point to a more natural, yet profoundly distant source. One compelling possibility is that we are witnessing the final moments of an interstellar traveler. Picture a massive comet, perhaps 100 times larger than Halley's Comet, on a long journey from another star. As it drifts into the inner reaches of a foreign solar system, the increasing heat from an alien sun begins to stress its ancient structure. The nucleus, a fragile agglomeration of ice and rock held together by little more than its own cold, starts to crack. Suddenly, a huge fragment shears off, a chunk the size of a mountain breaking free. For a brief moment, as this newly exposed surface rotates into the sunlight, its pristine ice acts like a perfect mirror. From our vantage point light years away, we see not a comet, but a single, dazzling point of light, a flash as this colossal ice mirror reflects a star's rays directly at Earth. Then, just as quickly, the fragment tumbles, the reflective angle is lost, and the light winks out. The comet continues on, now slightly diminished, leaving behind no trace but that one recorded flash in our data. An even more catastrophic version involves total disintegration. Some comets, especially those on their first plunge toward a star, are known to fall apart completely. If an interstellar comet were to undergo such a violent disruption, the cloud of icy debris would present a vast, chaotic array of reflective surfaces. Sunlight scattering through this cloud could produce not one flash, but a rapid series of them, a flickering strobe effect that might last for several minutes before the debris disperses and darkens. These flashes would be a silent, luminous signal of a death occurring light years away. The challenge is separating this cosmic signal from terrestrial noise. Advanced surveys like the Panoramic Survey Telescope and Rapid Response System, or PAN-STARRS, are designed to filter out known satellites and space junk. When an unexplained flash passes these filters, appearing in a region of sky far from common satellite orbits and matching no known asteroid or comet track, it becomes a candidate for something far more exotic. The true test would come from a coordinated follow-up. If multiple telescopes around the world could be alerted in real time to catch the afterglow or any residual debris cloud, they might detect a faint, expanding haze or a specific chemical signature in its light, the ghost of a comet's coma. So far, no such observation has been conclusively made, leaving these optical flashes as tantalizing, unresolved entries in astronomical logs. They are the universe's momentary winks, brief and brilliant hints that somewhere, in the vast dark between the stars, something frozen and ancient has just come apart, sending us a final, silent signal written in a language of pure, reflected light. A silent flash of light is a momentary farewell, but some particles carry their message straight through the heart of our planet. Deep in the Antarctic ice lies one of science's strangest observatories, IceCube. It is not a telescope of glass and mirrors, but a grid of over 5,000 sensitive light detectors buried more than a mile beneath the surface, frozen into a cubic kilometer of pristine ice. Its purpose is to catch the ghosts of the universe, neutrinos. These are the most elusive particles known, tiny, nearly massless entities that fly through planets and stars as if they were empty space. Trillions pass through your body every second without a single interaction. IceCube waits for the exceedingly rare moment when one of these cosmic phantoms, usually from a distant supernova or a black hole's jet, strikes an atom in the ice, producing a faint blue flash of light called Cherenkov radiation. The detector maps these flashes, tracing the neutrino's path back to its origin in the cosmos. Now consider an interstellar comet unlike any we have imagined. Picture a wanderer that formed in the debris cloud of a cataclysmic stellar explosion, a supernova. Within its icy matrix, it could carry tiny but significant amounts of rare radioactive isotopes forged in that stellar fire, like aluminum-26 or beryllium-10. These unstable atoms decay over time, and as they decay, they emit particles, including, very occasionally, neutrinos. For most of the comet's lonely journey, this decay is a slow trickle, an undetectable whisper lost in the cosmic background. But as it swings perilously close to our sun, something changes. The intense solar radiation and heat could potentially accelerate certain decay processes or even fracture the comet's interior, exposing fresh reservoirs of radioactive material to space. This could trigger a brief, faint surge in neutrino production, a tiny burst of these ghostly particles emanating from the comet itself. For just a few days or weeks, this icy visitor would become a pinpoint source of neutrinos, a moving dot in the sky not of light, but of the most shadowy particles in existence. The signal in Ice Cube would be subtle, almost impossibly so. It would not be a single, brilliant flash. Instead, it would manifest as a slight statistical excess of neutrino events coming from a very specific, and more importantly, moving patch of sky. The detectors would see a handful more of those characteristic blue flashes than background models predict, all clustered along the comet's projected path. The challenge is monumental. The neutrino background from other cosmic sources is immense and noisy. Disentangling a few extra flashes from a moving point source would be like trying to hear a single whispered sentence in a roaring football stadium. It would require knowing exactly where to look and when, and even then, the evidence would be statistical, a compelling maybe rather than a definitive yes. Yet the implications are staggering. If such a signal could ever be teased from the data, it would not just identify an interstellar comet. It would chemically dissect it from a distance, proving it carried the radioactive ashes of a dead star. This wanderer would be more than a messenger. It would be a piece of stellar fallout, a radioactive relic sailing the cosmic seas, announcing its passage with the faintest pulse of particles that barely acknowledge the existence of matter. Neutrinos pass through planets like ghosts, but magnetic fields shape the very space around them. Our sun generates a vast, invisible bubble of magnetism called the heliosphere, which stretches far beyond Pluto. Within this bubble flows the solar wind, a stream of charged particles carrying the sun's magnetic field lines outward like an immense spiraling web. When a normal comet enters this system, a beautiful and predictable dance begins. The comet's neutral gases become ionized by sunlight, turning into a plasma. This plasma, being electrically charged, cannot cross the sun's magnetic field lines. Instead, it captures them. The solar magnetic field drapes itself around the comet's atmosphere, forming a magnetic envelope that can stretch for millions of miles, sculpting the ion tail into that characteristic straight blue line. Sometimes this interaction becomes too intense. A shift in the solar wind can cause these draped field lines to snap and reconnect in a process called a tail disconnection event, literally blowing the comet's ion tail away into space, only for a new one to grow in its place. These are known natural signatures in our magnetic field data, but what if the visitor brought its own powerful magnet? Imagine an interstellar comet with a secret heart. Instead of a porous mix of ice and rock, its nucleus contains a dense metallic core rich in iron, a remnant from the core of a shattered protoplanet in its home system. This ferrous heart, frozen and silent, could retain a strong, intrinsic magnetic field, a fossilized imprint of its violent past. As this magnetic comet plows into our heliosphere, the interaction would be anything but graceful. It would not simply drape the sun's field lines, it would fight them. The comet's own persistent magnetic field would act like a blunt object moving through a stream of water, creating turbulent wakes and eddies in the interplanetary magnetic field. Probes like NASA Voyager or the Solar Terrestrial Relations Observatory, which constantly monitor the solar wind, would record a highly localized region of magnetic chaos. The data would show a moving point of intense distortion, where the strength and direction of the magnetic field fluctuate wildly and illogically. It would look like a magnetic storm the size of a planet, but one moving on a precise, hyperbolic trajectory that defies all models of solar weather. This anomalous knot of distortion would be a clear signal with no natural explanation within our solar system. We have no known objects, no asteroids or comets of local origin, with magnetic fields powerful enough to create such a pronounced disturbance. Detecting this signal would be like hearing a familiar symphony suddenly interrupted by the blast of an unseen horn, playing in a key that does not belong. It would tell us that the visitor is not just a simple ball of ice, but a world with a hidden, metallic history, a fragment of a failed planet from another star, announcing its presence by violently rearranging the invisible architecture of our own sun's domain. A magnetic storm reveals a comet's hidden heart, but sometimes the most telling signal is the absence of any storm at all. Far beyond the orbit of Neptune, in the frozen depths of our solar system's Oort cloud, astronomers recently discovered a behemoth. Comet C/2014 UN-271, known as Bernardinelli-Bernstein, is a true giant. Estimates suggest its nucleus could be over 80 miles across, making it perhaps the largest comet ever identified. Based on everything we know, a comet of that size, even at its great distance, should be a hive of subtle activity. The faint heat from the distant sun should be enough to vaporize the most volatile ices on its surface, like carbon monoxide, creating a faint but detectable halo of gas and dust. Yet when telescopes turned their gaze to this monster, they saw almost nothing. It was a dark, silent mountain drifting in the perpetual twilight. This profound quiet is its own kind of signal, a message written in the absence of expected noise. For a comet born in our own solar system, this silence is deeply puzzling. It suggests a surface that is either incredibly old and depleted, or sealed beneath a thick, dark crust of organic gunk that acts like a cosmic insulator, trapping its volatile ices inside. Now translate this mystery to an interstellar scale. Imagine a Bernardinelli-Bernstein from another star, a wandering giant on a hyperbolic path. Its sheer size would make it a prime candidate for spectacular activity as it neared our sun. We would expect it to become the comet of the century, a blazing spectacle with a tail stretching across the heavens. But what if, as it swung through our inner solar system, it remained as stubbornly quiet as our own distant giant? That silence would be a deafening signal. It would tell us that this traveler came from a place of profound and enduring cold, far colder than even the outer reaches of our solar system. In such an environment, the comet's ices would not be the relatively volatile mixes we know. They might be dominated by substances like nitrogen or methane, which only become active at temperatures much closer to the sun. Or its entire crust could have been annealed and hardened by eons of exposure to the harsh radiation of interstellar space, creating a uniform, non-porous shell that no solar heat can easily crack. An interstellar mega-comet's silence could also hint at a catastrophic past. Perhaps it suffered a glancing collision or an extreme tidal encounter with a planet in its home system long ago. That event could have flash-heated its surface, melting the outer layer into a solid, glassy crust that permanently sealed the interior. The comet would become a cosmic thermos bottle, its ancient ices perfectly preserved but utterly hidden. This kind of signal forces us to listen differently. We are accustomed to searching for flashes, pulses, and chemical signatures, but the quiet giant teaches us that sometimes the universe communicates through what it withholds. A massive interstellar visitor that should roar but instead remains mute is carrying a story of deep, cold, violent history or exotic chemistry. Its silence is not an empty void. It is a detailed report on the conditions of its birth and journey, a puzzle where every expected piece of data is conspicuously missing, and that absence speaks volumes. Silence from a giant is one form of evidence, but sometimes the proof is microscopic. For decades, scientists have attempted to catch the smallest messengers from the stars. NASA's Stardust mission was a daring endeavor, launching a spacecraft equipped with a tennis racket-sized collector tray filled with a substance called aerogel. This ultra-light, porous material was designed to be a cosmic flytrap, gently capturing particles without destroying them. The primary target was dust from Comet Wild 2, but Stardust also had a second, more ambitious goal. On its journey, it pointed another collector panel toward the stream of interstellar dust that flows through our solar system, hoping to catch pristine grains from between the stars. The mission was a success, returning its precious cargo to Earth in 2006. Researchers have since been painstakingly analyzing the microscopic tracks and particles embedded in the aerogel, identifying a handful of likely interstellar candidates. These specks are smaller than the width of a human hair, yet they carry elemental stories from other stars. Now, consider a more dynamic and puzzling scenario. Imagine a future spacecraft equipped with sensitive impact detectors, not just passive collectors orbiting Earth or traveling through deep space. Suddenly, its sensors record a tiny but unmistakable ping. A microscopic particle, perhaps only a fraction of a millimeter wide, has slammed into the hull at an astonishing speed, far greater than the typical drift of interstellar dust. The impact vaporizes the particle instantly, but the detector captures crucial data: its velocity, its angle of approach, and even a spectral hint of its composition from the flash of vaporization. The numbers tell a strange story. The particle's trajectory is hyperbolic, meaning it is not orbiting our sun, it is just passing through. Its speed is not just interstellar, it is extreme, as if it was launched like a bullet. And its composition shows a mix of silicates and complex organic molecules, a signature reminiscent of cometary dust, but with isotopic ratios that are subtly off. This microscopic signal could be a clue to a macro-scale mystery. The leading theory would point to an unseen parent body, an interstellar comet traveling somewhere on the fringes of our solar system. As that comet underwent a violent outburst, perhaps triggered by a crack in its nucleus or a sudden exposure to solar heat, it would have ejected a jet of gas and dust into space. Within that jet, the smallest dust grains, unimpeded by significant gravity, could be accelerated to tremendous speeds, far outpacing the comet itself. This tiny particle that struck our spacecraft would be a single piece of shrapnel from that distant explosion, a solitary messenger sent ahead of the main event. It is a cosmic warning shot. Detecting such an anomalous impact would immediately trigger a hunt. Astronomers would trace the particle's path backward, searching the vastness of space along that line for any hint of a faint, moving object. They would be looking for the source, the comet that fired this microscopic bullet. Finding it would be a triumph of forensic astronomy, using a speck of dust to locate a hidden wanderer. But even if the parent body remained hidden, the particle itself would be a treasure. Its high velocity and unique composition would be a direct sample of an interstellar comet's interior, material that has never been altered by our sun's heat or gravity. It would be a signal not of light or radio waves, but of pure physical presence, a piece of another star system delivered to our doorstep by the explosive force of the comet it once called home. The search for extraterrestrial intelligence has always listened for signals that stand out from the cosmic noise, for a narrow, deliberate whisper in the radio static. These narrowband transmissions are the holy grail of SETI, a sign of technology because nature almost never produces such a clean, focused radio tone. But what if that perfect signal did not come from a distant star, but from something moving through our own celestial neighborhood? This leads to a provocative and elegant hypothesis. an advanced civilization might use interstellar comets as natural spacecraft or hiding places. A comet is, after all, a ready-made vessel. It contains water ice for fuel and life support, complex organic molecules for chemistry, and a thick, dark nucleus perfect for shielding sensitive equipment from radiation and prying eyes. A probe hidden within, or even constructed from, the comet's materials could lie dormant for eons, its systems powered by the slow decay of radioactive isotopes, waiting for the gravitational nudge of a star system to wake it up. Once active, such a probe could use the comet's own volatiles to power a transmitter, sending out a brief, powerful, narrowband signal. To our telescopes, this would appear as the ultimate unexplained signal. We would detect a moving point source, the comet itself, emitting a radio tone of astonishing purity. The signal would be locked to one precise frequency, unlike the messy broadband crackle of natural plasma emissions. It would follow the comet's hyperbolic trajectory across our sky, a beacon that moves with the object, proving the transmission is not a glitch or a distant star, but is intimately tied to the wanderer itself. The implications are staggering. A narrowband signal from a comet would check every box for a sign of artificial intelligence while bypassing the immense energy requirements of interstellar broadcast. It would be a message in a bottle, a targeted communication aimed not at a star but at the planets orbiting it, delivered by a celestial postman. We have never detected such a thing, but the idea reframes how we might listen. SETI surveys typically stare at distant stars for long periods. A comet-borne signal would require a different strategy, monitoring known hyperbolic objects as they pass, listening for that perfect, unnatural tone amidst their natural radio whispers. It suggests that the most profound message we might ever receive could be transient, attached not to a fixed point of light, but to a silent, dark traveler finally announcing it was never alone. A comet's tail is its most iconic feature, a luminous brushstroke across the dark canvas of space. But sometimes that brushstroke breaks. Astronomers call these tail disconnection events, and they are a ghostly spectacle. A comet's straight, blue ion tail, sculpted by the solar wind, can appear to snap clean off and drift away while a fresh tail grows in its place. This is not an illusion, it is a fundamental restructuring of the comet's magnetic environment. When a sudden surge in the solar wind, perhaps from a coronal mass ejection, hits the comet, the draped magnetic field lines around it can violently reconnect. This magnetic snap severs the ion tail, releasing it to drift downwind like a phantom banner. For comets in our own system, these events are dramatic but understood, a natural part of living in the Sun's turbulent atmosphere. An interstellar comet, however, would experience our solar wind as a foreign and chaotic sea. It has spent eons bathed in the stellar wind of its native star, a flow with a different speed, density, and magnetic character. When this stranger plunges into our heliosphere, the interaction would not be a familiar dance, but a collision of invisible forces. The result could be a tail phenomenon of bizarre and extreme proportions. Instead of a clean disconnection, we might witness multiple ghost tails appearing simultaneously, pointing in conflicting directions as the comet's ionized gas gets caught in competing magnetic eddies. The tail might not point directly away from the Sun at all, but kink at a severe angle or even appear to point toward the Sun, creating a visually impossible and haunting image. This ghost tail would be a direct optical signal of profound magnetic confusion. It would be the comet's atmosphere literally lost in translation, unable to align with the unfamiliar rules of our Sun's domain. Observing such an event would be like watching a ship from a distant land try to sail in our waters with a compass calibrated for another world, its sails luffing in a wind it cannot comprehend. The ghost tail is more than a strange sight. It is a live diagnostic of the interstellar medium itself, a fleeting experiment that reveals how the magnetic character of one star system differs from our own. A ghost tail reveals magnetic confusion, but light can dissect a comet's very soul. Spectroscopy is the art of listening to that light, of breaking a comet's glow into a rainbow and reading the dark lines where specific molecules have stolen away specific colors. Each line is a chemical signature, a fingerprint left in stolen starlight. For decades, we have catalogued the familiar fingerprints of our own solar system's comets: water, carbon dioxide, cyanogen, and simple organics. But an interstellar comet carries the chemical library of another star. When our telescopes turned their spectrometers toward Comet Borisov, they saw the expected lines, but they also saw faint, unfamiliar shadows in the light. These were spectral whispers of molecules we could not immediately identify: complex carbon chains and exotic ices. The true revolutionary signal would be far more pronounced, a set of spectral lines that do not match any molecule in our earthly databases. This is the dream of astrochemistry, to find a compound in space that our own solar system never cooked up. Imagine an interstellar comet that, as it nears our sun, begins to vent not just water and carbon monoxide, but a rich stew of prebiotic molecules. These are the building blocks of life, amino acids or nucleobases, but arranged in a slightly different way, or in abundances that seem impossible under our local conditions. Their spectral fingerprints would appear as a cluster of strange, new lines in the infrared or millimeter wave spectrum, a barcode we have never scanned before. Decoding that barcode would be a task for supercomputers and laboratory scientists, who would try to recreate the conditions of an alien protoplanetary disk to see what molecule could possibly produce such a pattern. The implications are profound. Such a signal would be a direct chemical message from another star's nursery, proving that the pathways to complexity, perhaps even to the precursors of life, are not unique to our little corner of the galaxy. It would tell us that the universe's chemistry set is far larger and more inventive than we ever assumed. This would not be a signal of intelligence, but of fundamental potential, a quiet announcement that the ingredients for whatever comes next are sown across the light years, waiting on the backs of dark, icy travelers. An object's path through the heavens is its most fundamental statement. Every curve, every loop is a story written in the language of gravity, a perfect record of every push and pull it has ever experienced. For comets born in our solar system, that story is an elliptical loop, a closed orbit that always brings them home to the sun's embrace, even if the journey takes millions of years. The orbits of our first two interstellar visitors, Oumuamua and Borisov, told a radically different tale. Their paths were not loops but open-ended hyperbolas. They were not coming home, they were just passing through, moving far too fast to ever be captured by our sun's gravity. That hyperbolic trajectory was the first and clearest signal of their alien origin, a cosmic speed limit stamp on their passport. But what if we one day intercept a comet whose orbit is not just hyperbolic, but paradoxically so? Imagine a future object that enters our solar system on a path so extreme it defies simple explanation. Its speed and angle suggest it was flung here not by the gentle drift of interstellar space, but by a violent, close-range event. One possibility is a gravitational slingshot from an unseen planet orbiting another star. In our own system, we use the gravity of planets like Jupiter to fling probes to the outer solar system, adding tremendous speed. An interstellar comet could have made a daredevil pass close to a giant exoplanet in its home system, a gas giant many times the mass of Jupiter. That encounter would act like a cosmic catapult, hurling the comet away at such velocity that it broke free of its star entirely. The orbit we would observe would carry the precise mathematical signature of that launch, allowing us to backtrack not just to its home star, but to the specific giant planet that expelled it. We could, in essence, discover an alien world by studying the trajectory of the bullet it fired. An even more dramatic origin story is written in a truly impossible orbit. What if a comet's path indicates it came not from the quiet disk of a star system, but from the chaotic maelstrom right next to a star, A comet that skimmed the scorching corona of a red giant or passed through the fierce stellar wind of a blue supergiant would experience forces beyond mere gravity. Intense radiation pressure and plasma drag could alter its course in ways that leave a bizarre orbital fingerprint. The trajectory would be hyperbolic, yes, but with a strange kink or an anomalous change in velocity that pure gravity cannot explain. It would be the signal of a solar furnace, a visitor that survived a brush with stellar fire. The ultimate paradox, however, would be an orbit that seems to come from nowhere. The mathematics would trace its path backward into empty interstellar space, with no star system along the line for millions of years. This would suggest the comet has been traveling for longer than the typical lifetime of its icy constituents, or that it was accelerated by something we cannot see. Perhaps it was nudged by the subtle gravity of a rogue planet, a dark world drifting between the stars, or even by the concentrated mass of a dense clump of dark matter. Such an orbit would be a profound celestial mystery, a path that points to the invisible architecture of the galaxy itself. The orbital paradox teaches us that a comet's journey is its loudest signal. We do not need to hear its radio whisper or decode its chemical signature first. By simply watching its arc across our sky, we can read a history of cosmic violence, of hidden planets, and of close calls with alien suns, a biography written not in words but in the immutable curves of space and time. The mathematics of an orbit traces a grand history, but a single radar ping can reveal the shape of the present. As our final interstellar messengers arrive, the most powerful tool we have to meet them is not a telescope that collects light, but a radar that creates it. Facilities like the now-lost Arecibo Observatory and NAS, a Goldstone deep space communications complex, act as cosmic flashlights. They fire a concentrated beam of radio waves into the dark, then listen with exquisite patience for the faint echo that bounces back. By measuring the delay and distortion of that return signal, supercomputers can construct a three-dimensional shape model of a distant asteroid or comet, revealing craters, ridges, and even spin rates from hundreds of millions of miles away. It is the closest we can get to touching these objects without a spacecraft. For a local asteroid, the results usually show a lumpy, potato-shaped world, a testament to a violent history of collisions. But the echo from an interstellar visitor could tell a profoundly different story. Imagine the moment when the first detailed radar images of such an object are processed. The data resolves not into a familiar, irregular lump, but into a shape that defies all expectations of natural geology. It could be a perfect sphere, smoother than any known celestial body, its surface seemingly polished by forces we cannot comprehend. Or it might appear as an extreme needle, a shape so elongated and uniform it challenges the very physics of how rotating rubble piles hold together. Most provocative of all would be a structure with clear, repeating symmetry, like a series of aligned cylinders or facets that catch the radar beam and return flashes of impossible geometry. This radar echo would be more than a picture, it would be a direct signal of form, a silhouette against the void that screams of anomaly. The immediate debate would ignite, splitting the scientific community and captivating the public. Natural explanations would be pushed to their absolute limits. A perfect sphere might be explained as a once molten object that cooled in the deep vacuum of interstellar space, where surface tension could dominate without gravity to distort it, but the likelihood is vanishingly small. An extreme needle shape could be the remnant of a catastrophic tidal disruption, where a larger body was stretched apart by a black hole or neutron star, yet surviving such an event intact seems miraculous. Symmetry is the greatest puzzle of all, as nature abhors perfect repetition. The most ardent defenders of natural processes would propose exotic ices with crystalline structures on a planetary scale, or the chance alignment of several separate objects flying in precise formation. Yet the shadow of the artificial would be impossible to ignore. A perfect sphere is the most efficient shape for a pressurized vessel. An elongated needle minimizes cross-section for a high-speed journey through interstellar dust. Symmetry is a hallmark of design, of engineering for a purpose. This radar return would force us to confront the possibility that we are not looking at a rock, but at a craft, a probe designed for the long dark between stars, its form optimized for survival in ways nature never required. The signal would be a single, powerful echo asking the oldest question in a new and urgent way: are we alone? And the answer would not come from a radio message, but from the cold, hard geometry of a silent traveler, its shape a wordless argument written in the language of physics itself. A perfect geometric echo would be a singular shock, but the universe's greatest mysteries are rarely so isolated. The ultimate unexplained signal would not be a single whisper, a lone flash, or a strange shape. It would be a pattern emerging from the noise, a connection between events we thought were random. Imagine if we could step back and view the entire catalogue of these anomalies not as 24 separate puzzles, but as pieces of a single, sprawling mosaic. What if the faint radio shrieks, the anomalous radar glitches, the unexplained optical flashes, and the bizarre chemical signatures all began to align? Not by chance, but along a hidden axis, scientists could take the dates and directions of every major unexplained signal tied to interstellar objects or candidates and plot them against the vast architecture of our galaxy. The result might reveal a chilling correlation. Perhaps these signals cluster along a specific plane of the Milky Way, a dense spiral arm rich with star formation and supernova remnants. This would suggest the comets and their strange emissions are not random wanderers, but refugees from a specific, violent region of the galaxy, a cosmic factory producing anomalous travelers. Even more profound would be a temporal pattern linked to galactic events. Do these signals spike in the years following a known nearby supernova, whose shockwave could have shaken loose a swarm of ancient comets from the Oumuamua clouds of distant stars, sending them on paths that eventually cross our own? Or could they correlate with the solar system's periodic passage through dense interstellar clouds, events that happen every few tens of millions of years? In such a cloud, our sun's heliosphere shrinks and interstellar material presses closer. This could trigger outbursts from dormant interstellar comets already lurking in our outer solar system, or increase the rate at which new ones are captured, leading to a temporary surge in all the strange signals they produce. The meta-signal, the pattern itself, would be the most powerful discovery of all. A random scatter of anomalies is just cosmic static, but a pattern is a message. It could point to a coordinated natural phenomenon on a scale we barely comprehend, a galactic weather system that periodically sends storms of icy messengers our way, each one ringing its own peculiar bell as it passes. Or, in the most mind-bending scenario, the pattern could hint at something more. If the signals showed a timing or directional alignment that defied natural astrophysical cycles, if they seemed to follow a logic or a sequence with no clear physical driver, we would be forced to confront a staggering possibility. It would suggest that the phenomena we've catalogued, the shrieks, the whispers, the ghost tales, are not just accidental byproducts of natural comets, they could be signatures. They could be the varied emissions of a fleet or a network of engineered objects using comets as both camouflage and carrier, following a mapped course through the galaxy and checking in with signals we are only now learning to hear. This pattern would be the universe's grandest symphony, composed not of notes but of mysteries, each one a measure in a score we have just begun to read. It tells us that the greatest signal may be the connection between signals, a hidden order in the celestial chaos, waiting for us to finally see the whole picture. That hidden symphony of signals is about to become a roar. The hunt for interstellar messengers is on the cusp of a revolution, powered by a new generation of eyes and ears that will scan the heavens with unprecedented depth and speed. The Vera C. Rubin Observatory, poised to begin its decade-long legacy survey of space and time, will not just look at the sky, it will watch it, Every few nights, its massive mirror and gigapixel camera will capture the entire visible southern sky, not once but over and over. This relentless stare will catch anything that moves, flickers, or changes. Where current surveys might spot one interstellar visitor every few years, Rubin is predicted to find dozens, perhaps even hundreds. It will find them earlier, fainter, and farther out, giving us precious time to train every other telescope on Earth on these fleeting guests. We will no longer be relying on chance discoveries by dedicated astronomers or lucky amateurs. We will have a systematic census of the strangers passing through our solar neighborhood. At the same time, the square-kilometer array, a forest of radio antennas spanning continents, will listen with a sensitivity 100 times greater than today's best instruments. It will hear the faintest whispers, the most subtle periodic pulses, and the briefest shrieks from comets so dark and distant they are invisible to optical light. This vast radio ear will map the magnetic chaos around these objects in real time, potentially picking up the structured radio tones of narrowband signals that have, until now, been lost in the static. Together, these tools will transform interstellar objects from rare curiosities into a statistical population. We will learn their typical sizes, their speeds, their directions of origin. We will begin to see patterns in their chemical compositions and the signals they emit. But the ultimate dream goes beyond observation from a distance. Space agencies are already drawing up plans for a mission that would not just watch, but meet one of these travelers. Imagine a spacecraft parked in a holding orbit, ready at a moment's notice to launch on an intercept course with a newly discovered hyperbolic object. Using advanced propulsion, it could rendezvous with the comet, flying alongside it to directly sample its ices, map its surface with radar, and measure its magnetic field without the filter of Earth's atmosphere. Such a mission would turn every unexplained signal into a solvable equation. Is that radio whisper from a natural plasma process or something more? A sensor at the source could tell us in an instant. Does that strange spectral line belong to an unknown organic molecule? A mass spectrometer could identify it atom by atom. The very act of chasing down an interstellar object would be humanity's first step into the cosmic ocean, a deliberate mission to meet a messenger from another star. This coming flood of data means one thing with absolute certainty: the catalog of unexplained signals is poised to explode. For every mystery we solve, like the true nature of Oumuamua's acceleration, 10 new and deeper mysteries will likely take its place. We will find objects that make our first 2 visitors seem utterly ordinary. We will record signals that defy our current categories of natural phenomena. The biggest puzzles, the most profound anomalies, and perhaps even the answer to whether we are alone in this great dark sea, are almost certainly still ahead of us, waiting in the silent drift of the next icy wanderer to cross the threshold of our sun's light. The journey through these 25 signals reveals a universe speaking in a symphony of strange tongues. We have heard the radio shrieks of dying ice and the faint, ticking heartbeat of a comet's spin. We have decoded chemical fingerprints written in alien isotopes and watched ghost tales point in impossible directions. We have traced orbital paradoxes back to unseen planets and imagined echoes bouncing off dark geometric shapes. Each signal, from the subtle whisper to the deafening silence of a giant, is a piece of a grander puzzle. Interstellar comets are far more than simple icy rocks. They are archives, they are cosmic forensic samples carrying within them the temperature of their birth cloud, the magnetic storms of their home star, and even the radioactive ashes of stellar explosions. They are messengers, and their language is written in light, in radio waves, in chemistry, and in the very fabric of space-time. For centuries, we looked up at the stars and wondered if we were alone. Now, we realize the answer might not come from a distant, fixed point of light, but from a dark, silent traveler passing through our own backyard. The universe is talking, weaving its stories into the ice and dust of these nomadic wanderers. We have built the ears to hear their whispers and the eyes to see their faintest glimmers. We are, as a species, just learning how to listen. So tell us, which of these cosmic signals captured your imagination the most? Was it the haunting possibility of the wow signal being a celestial echo, or the profound silence of a dark giant holding its secrets tight? Share your thoughts below, and if you are captivated by the mysteries waiting between the stars, subscribe. Our journey to decode the universe's messages has only